Got a big one today. Today we're going to look at some real calculus here. We're going to tackle the derivative power rule, one of the most important and definitely one of the most widely used, rules in calculus. The derivative power rules, again, a shortcut. I briefly mentioned it in the limit definitions of a derivative video. This is what I talk about when I say that there is a shortcut that lets you skip all of that derivative or that limit evaluation stuff, right? So with all of that, we're going to discuss the power rule, probably one of the most powerful shortcuts in all of calculus. Let's begin. Now, textbook definition. You will see in books, from professors, from teachers, what I'm about to show you as the formula for the derivative power rule, right? And this all comes from mathematicians a long time ago, doing a lot of limit definition of a derivative problems and finding patterns, really convenient patterns, right? So if you remember from our function notation video, here I'm actually going to use the ddx notation. I know I said I wouldn't use that much, but here it's a good representation. If you remember that video, I told you about how usually when mathematicians are showing formulas and descriptions of stuff, they will use the ddx notation because here it makes sense, right? You could also just say, let's say f of x equals x to the n, right? And then f prime of x would equal, and we're getting to that here. First, let's resume with the top here. So we use multiple colors. The derivative of x to the nth power, and n can be any number, right? Any integer value, not a variable. N is not a variable. There are different rules for that we'll go over much later. But for now, n is a number, right? And I'm going to highlight that n in blue. You'll see why in a second, right? That the derivative of x to the nth power, where n is a number, is equal to n times x to the power of n minus 1. And that's a quantity right there, right? And now, I use the same n for all three of those. That n that I underlined in blue is equal to this n and this n. They're all the same n. They're all the same number, right? Now, at first, it looks kind of confusing, and I'll bring the camera up so you can see that. That's your textbook definition of what the derivative power rule is, right? That's kind of confusing to think of, right? We don't have any numbers. Usually when we're dealing with numbers, or derivatives, we're dealing with functions and numbers and calculus and all of that. But this is just a bunch of x's and n's. So how does that make sense, right? And here with the f prime notation, I'll write the same thing. Because remember, the function notation does not actually change the output value of a derivative. Okay, now, the best way, I believe, to think about this derivative power rule, right? And I'll leave this up for the whole video, because this is the textbook definition of the derivative power rule. But I think the best way to express it is through examples, but focused examples, right? This is the way, and I'm about to show you the way I think about the derivative power rule, and I think it makes most sense. I don't like to think of this n stuff gets kind of confusing. I like to have this visual, right? I'm going to say, let h of x equal x to the third power, x to the third power. And I'll write that more clearly. X to the third power, right? Now, the way I think about this is you just take this number, you bump it out in front of the x, and then you subtract 1 from the power. Really that easy. So if h of x equals x cubed, then h prime of x equals, and then bump that 3 out in front, 3x, subtract 1 from the power, 3 minus 1 is 2. So that's 3x squared. Boom. You just did calculus. That is calculus. That's it, right? And now, again, reviewing our function notation, derivative notation video, you are not allowed to say, I'll write this in red, equals 3x squared, right? That's not true. X cubed does not equal 3x squared. H of x equals x cubed, and h prime of x, the derivative of h of x, equals 3x squared. So don't write this. This is not true. Make sure you're always using your correct function notation, right? You don't want to write something that's mathematically incorrect. So with that out of the way, we'll do an example problem. Pretty simple one, very similar. We're using x to the fifth, right? Another polynomial function, just single variable though. So it's still relatively simple. And I'll solve this next one in red. Right. If f of x equals x to the fifth, then f prime of x, because remember we're using our function notation, equals, I'll let you think about that one for a second. What are we doing? We're taking this 5, we're bumping it out in front, and we are subtracting 1, right, from the power. So that's going to be 5x to the, and then 5 minus 1 is 4, so to the 4th power. You just did calculus, just like that, that easy, right? We'll get here in a little bit. So beforehand though, I'd like to remind you that, remember, derivatives find us instantaneous slopes at any given point, right? So at any given point on the function f of x equals x to the 5th power, if you were to draw out that graph, right, the slope, the instantaneous rate of change of that function, which is a little weird to think about, but as we go further, it'll start to make more and more sense, right? The instantaneous rate of change of that function, how it is increasing or decreasing or staying the same, is going to be represented by this function. If you could plug in a point to this f prime of x, so let's say you plug in f prime of 2, you evaluate that, meaning that you just found the instantaneous slope or rate of change of x to the 5th at x equals 2. I'll say that again. If you plug in f prime of 2, you evaluate this, you found the instantaneous slope, the derivative, of x to the 5th, the original function, at x equals 2, right? Kind of confusing to think about at first, right? But once we start getting to the applications of these slopes, it'll make a lot more sense, trust me, right? So now we have a few more things to tackle. If you remember all the way back to our limit laws video, I said that we are going to use the limit laws and forget about them, and we are going to use them without even thinking about them. And that is true, right? So the next thing I'm going to show you is kind of another example over on the side of the board. Let's say we have g of x equals, let's go, x to the 5th plus x to the 3rd, right? Now what we see is that there's only one term in this. So how do we take the derivative of this function? Well, it's really as simple, and I forgot to write my function notation again. It's really as simple as, you take the derivative of each term independently. So this would be, again, 5x to the 4th plus, and then 3x squared. And I'll show you why this works, and it relates to the limit laws, right? So what we are doing here is we are taking the limit, as your delta x approaches 0 of, and then this function here, x to the 5th. Oh, we have to write out the difference quotient, my bad. So it's going to be x plus delta x to the 5th plus x plus delta x to the 3rd minus, and then over here in brackets, x to the 5th plus x to the 3rd, right? You can see why we use this power rule now. Very confusing, and all that's over delta x, right? And so now, if we don't think about this denominator right now and we just zoom in on this numerator, right? Really zoom in on this. What do you see? I see a bunch of addition. I see addition and I see subtraction, right? So, long story short, you can use the quotient derivative rule to get this delta x out, right? So you'd have, I'm not going to write this out again, the limit as delta x approaches 0 of this whole numerator divided by the limit as x approaches 0 of this whole denominator. And then you have just a bunch of addition and subtraction in this top part here. So what you do is you use the sum and difference laws. And essentially all of this boils down to you are finding the limit definition of your derivative as x approaches 0, or delta x approaches 0, of your x to the 5th term, assuming that's the difference quotient, and your x to the 3rd term, assuming that's the difference quotient, and adding them together. You get really a limit plus a limit, right? Forgot to write it over here, and divided by another limit. And that's what you're doing. We're skipping all of this, Remember when I said in the limit laws video that we're going to use the limit laws without even thinking about them? Here we are doing that. We're doing a lot of limit laws stuff, a lot of algebraic manipulation of our calculus limits, right? And so you, in addition and subtraction, you can independently take the derivative of each and every term. And the limit laws kind of expand to what we call the derivative laws. Essentially, the less commonly known because they're widely assumed, right? Basically what that's saying is that the derivative of this x to the fifth plus x to the third would really just be the derivative of x to the fifth plus the separate derivative of x to the third, which is true. That's what we did here, right? So really, from now on, with addition and subtraction only, you can assume these to be independent. X to the fifth and x to the third, two totally separate functions. You take the derivative of each one, slam them together at the end, right? Into one big derivative function. Okay, and we'll do some examples with that later, as you see over here, right? But there's one last kind of derivative power rule, little special case that you need to know of. The derivative of a constant. And here again, I'm going to use the ddx notation. Because what if we did the derivative of 3 with respect to x, right? Now, let's look at this graphically first. If we had just the function y equals 3, right, on a graph, that'd just be a straight line, and out going to infinity in either direction. Now, remember what a derivative finds? It finds slope at any point. The slope at any point on this function is going to be 0, because this is not increasing or decreasing anywhere. So the slope here is going to be 0. So graphically, we can find that this derivative is equal to 0. But let's look at why that works according to our derivative power rule, right? And this is kind of a very creative and like tricky thing to think about. But what you're really doing here is, and I'm going to go down, I'm going to say, okay, let y equal 3, like we said on our graph. Well, what really is y equal to 3 mean? What does that mean, right? We can say in math that y is equal to 1 times 3. We can say it's equal to 1 times 3 to the first power. Because we haven't changed anything. We've just been multiplying by 1. And, technically the power on every constant is 1. You can do that, and it doesn't actually change the value of the constant. Here's the big one, why the power rule works for constants. It's because, I'll write it up here in red, because this is important, what you're really saying is that you have 3 times x to the 0th power. And this is the important part, x to the 0, because in math, anything to the 0th power is equal to 1. So what you really just wrote is that's equal to 3 times 1. But we have a variable in there, which is going to allow us to take the derivative using our derivative power rule. And you'll see here the application of that in a second. Now, if we know that the derivative of a constant is 0, but we also know that the derivative of 3 is going to be that derivative with respect to x of 3 times x to the 0th power, you don't usually write this out. That's a lot of work and it's confusing, and from now on it's going to be assumed because it's the reason why this power rule works. So what you're doing is you're taking this power of 0, you're bumping it out in front of 3x, and then you're subtracting 1 from the power. And so you get 0 times 3x, and then to the negative first power. Which, if you want to do some exponent manipulation there, that'd be 0 over x to the first power. And that's just equal to 0. You have this big old 0 that you just multiplied in front of your function, and that's going to cancel out the entire term. So the derivative of any constant by this derivative power rule is also equal to 0. So now we know how to graphically determine that, and now we also know how to, analytically, mathematically determine that with our calculus shortcuts, right? Okay, so if I were to ask you what the derivative, what the derivative here, and I'm using the ddx notation a lot, of 1,000 is, it's equal to 0. It's equal to 0. It's that easy. You just did calculus, just like that. So now in our next example, we're going to combine these two, right? I have written over here g of x equals 20 plus x to the 100th power. So we're going to combine our basic power rule using one term. We're going to combine that with our limit laws explanation of why we can take the derivative of a sum or the derivative of a difference and do those derivatives kind of independently of each other. And we're also going to combine that with the derivative of the constant. Okay, look at this function real quick. G of x equals 20 plus x to the 100th power, right? That's going to be equal to, we know the derivative of a constant is equal to 0. And because we can use our limit laws we use our limit laws to separate those terms and take the derivative of them each independently, this is going to be equal to, and now our process, take 100, bump it out, x, oh, I'm kind of infringing on my space here, and then we subtract 1 from that power, 100x to the 99th power. And that's it. Kind of writing small, so I'll show you that. Oh, making mistakes. I forgot to use my function notation. G prime of x. See guys, I forget this all the time too. Take a lesson from me. Don't forget to write your derivative notations. You figured it out, that's 0 plus 100x to the 99th power. All right, now we're talking real calculus. That's calculus, you just did that. Boom, easy. Now for our last example, we're going to combine all of it. Here, down at the bottom, I have y equals 4 times x to the 4th minus 3 times x to the 3rd power plus x squared plus 2x plus 0. Big polynomial function. But doesn't matter, we know how to solve it. Y prime. And you know, you can use the y prime notation, but here, because I've been using these other two, I'll use dy dx. dy dx equals, and then, okay, we're going to independently solve each of these derivatives and we're going to add them all together. 4x to the 4th. Okay, now this is kind of tricky. We have to bump that 4 out in front. So we have to multiply our x by 4. But it's already multiplied by 4. So what do? We just multiply the 4 by 4. We get 16x, and then 4 minus 1 is 3. 16x cubed is the derivative of that 4x to the 4th term. Now, minus, because our next term we're subtracting that, we take this 3, bump it out, multiply by the already existing 3 there, we're going to get minus 9x, and then subtract 1 from that power, squared. Boom. Okay, here we go over to x squared. That's an easy one. There's no constant out in front. We're adding 2x because we just bumped that 2 out in front, subtract 2 from that power, we just get 2x to the 1st power, which is just 2x. Then now, speaking of which, derivative of 2x. Okay, here's a weird one. Remember that x technically has a power of 1 on it, not power of 0. If it had a power of 0, that'd be a constant because that x would equal, that x to the 0th power would equal 1. But here, we have x to the 1st power because, you know, any variable existing on its own has a power of 1. We don't write it out, we assume it's there. So you bump out this 1, so we're just multiplying 2x by 1, and then we're subtracting 1 from the power. So this is kind of a weird one. We're going to get 1 times 2x to the 1 minus 1 power. And that's equal to 0, right? So now we do have x to 0. So you figured it out. The derivative of that is just equal to 2, because this whole thing right here becomes 1. X to the 0th power is equal to 1, and we're just left with 1 times 2 times 1, which is equal to 2. And so, boom. And now, derivative of 0. Here's an interesting one. We could go about this a few ways. One, you could just assume that that 0 is not there, because you're just adding 0, you're not really doing anything. But you can also treat 0 like a constant. You could say, okay, 0 is equal to 0x to the 0th power. And then the same thing holds true. You're bumping out that 0, you're subtracting 1, it's just 0. But I'm not going to write that out, because why would you write out plus 0? You don't need to. So, really, we took the derivative of that big polynomial function, and we get this other big polynomial function. This is a subtraction sign, minus sign, right? And really, That's the hardest calculus you will do with the basic power rule. You know, calculus gets a lot harder. There are other rules that we have to worry about, but this is probably the most widely used one. We use this within our other rules that we'll talk about soon, right? This really, really allows us to deal with polynomial functions especially, which in calculus are probably going to be our most commonly dealt with functions, right? So, and there are multiple ways to think about this. You could think about it using the N textbook definition, or you could think about it how I do, for example, where you really bump out that power out in front as a constant multiple, turn that exponent into a constant multiple, right? Then you subtract 1 from that exponent, and then boom, you have a derivative. And now I guess the next step is maybe if you're in a calculus class at this point, a textbook or an assignment might say, okay, now find the derivative of y with respect to x, or f prime of x when like x equals 2. So that'd be worded as f prime of 2. Or here's one that I forgot to note in my derivative notation video. This is an important one, so make sure you're tuned in for this. If there's no spot to plug in anything to this. We are not saying, you know, f prime of 2. How do we say f prime of 2? How do we plug in 2 to this? There's no like function input spot, right? Big thing here. To plug in something to dy dx, you draw a giant vertical line and write when x equals 2. Now you might have seen this in math before. You can do this anywhere. You can write this whole thing, write a giant line, x equals 2, and then plug in 2 to x. Boom. But really, you never do that. You never do that. You write dy dx when, and then this giant vertical line telling you to plug in x equals 2. That's what that line tells you to do, right? And that's the only way you can say that, hey, we are plugging in x equals 2. We are letting x equals 2 in this function, right? And now remember, writing this big giant line here, saying x equals 2 really is the same thing, because remember, dy dx equals all of this stuff. So we're doing just a giant substitution here. All right. Derivative power rule. Very, very, very important, right? If this is confusing, go over it. Find some other tools to help you master this. Do a lot of practice. Don't think about memorizing, you know, x to the n, the derivative of that is equal to n times x to the n minus 1 power. Don't think about that. Do examples. You will get so good at this so fast, you won't even have to think about it. You won't have to think about all the limit laws and the reason why we can separate our terms. You will not have to think about doing all of this weird substitution. You can just think about bumping out that power, right? It'll come so naturally to you, I promise. As we go further into the future, this will be the foundation of a lot of our calculus, right? So, really, thank you for joining me for this especially long video today. This is a very, very important one. Definitely be one of our longer videos in the whole subject of calculus. This is a very, very important introduction, right? I'll let you look at that for a second. Now, okay. If you want to practice this again, you can make up any function. As long as that is a polynomial function, you're not multiplying terms. So for now, you still don't know how to do the derivative of, 3x and then times, like, I don't know, x over, like 3x squared. You don't know how to do that yet. Don't try that. You don't know. Okay? Stick with simple polynomial functions. That'll help you learn the derivative power rule. It'll help you learn to add and subtract terms in your derivatives. You will get so good at this, I promise. Do not be afraid of it. So, again, thank you for joining me. Thank you for tuning in. All right, goodbye, class.